Okay, welcome to day 4 and of our turtle spotting expedition. Okay, so right, so last time what we saw is that we could encode the information about how the sheaf met the anticanonical curve, modulo these slightly annoying cases where the anticanonical curve is singular and your sheaf is badly singular there. Which we could always get rid of by nice monodromy transformation. So it's sort of just apparent. We could always, by blowing up our surface, separate the sheaf from the anticanonical curve. Okay, so in particular, what we see then is if we have a general rational surface, smooth projective rational surface, with a rational ruling on it. So that is a map to P1 such that the generic fiber is P1. Then there's a corresponding interpretation of sheaves on that surface disjoint from a chosen anticanonical curve as equations in this Higgs relaxation that have specified singularities. And these actually, so the precise singularities are specified in 2 ways. One is you have the surface, and the surface, it turns out, basically tells you the different irreducible singularities that appear. So for instance, one type of irreducible singularity for a differential equation is a rank 1 thing with a given exponent that's not 0. And then there's other more discrete data, which we'll talk about, which is basically the divisor class, the Chern class of the sheaf. And that specifies the multiplicities of these irreducible singularities. But before we can really talk about that too much, we need to say a little bit more about the structure of this situation. And in particular, we're going to need to understand what the combinatorial data is. In particular, what is the, how do we specify the divisor class of something on such a surface? Okay, so the first thing to note, well, so I've been talking about, the support of a sheaf. So let me make that more precise. So if M
haven't shared yet.
Oh, you mean it helps if I share the screen? All right. Luckily, I write loud so you can tell. Okay. All right. So if M is a sheaf on X with 1-dimensional support, then we define a subscheme support of M, but this is, I mean, there's the usual scheme theoretic support. This is a little bit better behaved. So let me call it F soup as follows. Choose a short exact sequence where V1 and V2 are vector bundles. So in other words, we're writing M as the co-kernel of the map of vector bundles. And of course, on our ruled surfaces, that's how we started with M. This is not an unreasonable thing. And in general, it's always going to be the case if it's 1-dimensional support and it has no 0-dimensional subsheaf. Which again is a reasonable thing to ask. Then it automatically has a homological dimension 1. So we just need to take any surjection from a vector bundle to M. The kernel will then again be a vector bundle, and this gives us our such a presentation. Okay, then F soup, and let me give this map a name phi. F soup of M is defined to be the scheme cut out. In particular, it's going to be a a Cartier divisor cut out by the equation that the determinant of phi vanishes. Now, this actually is independent of all the choices we've made. And so particularly, this is the zeroth fitting scheme, and so is independent of the choices. And then there's a discussion of this in Eisenbud's commutative algebra text, giant commutative algebra book. I just search for fitting, or I think it's in the index. But anyway, so in general, there's a sequence of schemes associated to any sheaf, which are somewhat better behaved than just say the scheme theoretic support. So in particular, the fitting support here has the property that so if you take a smooth curve in your surface, but M is a rank 2 vector bundle in that smooth curve, then the fitting support will be twice that curve as a divisor. Okay, and then the other observation is that the Chern class, first Chern class, is linearly equivalent to this fittings support. And this is what I mean by being better behaved. The fitting support, the scheme theoretic support can jump in flat families. The fitting support cannot jump in flat families, because the point is locally in a flat family, you can find a presentation like this where now V1 and V2 are flat families of vector bundles, and then take this divisor in a family, and it'll clearly be flat. So this is the right notion of support for our purposes. Okay, and what's nice here, this gives a map. Well, this induces a morphism because it behaves well in flat families from the moduli space of sheaves to the, well, moduli space of divisors, if you will. But the moduli space of divisors, of effective divisors, but the moduli space of effective divisors is a union over divisor classes of linear systems. So if we fix this Chern class, this is a map to a projective space. And just as a caveat, I'm assuming X is rational. Otherwise, I mean, you can still do things when X is not rational, but you have to take into account the fact that not only do you have a linear system, but you can also vary the actual line bundle. So the divisor class varies over a torsor of the Jacobian, and so you get a continuous degree of freedom from that, which is some abelian variety basically, and then a projective space over that, a projective bundle over that abelian variety, which are the linear systems. So it's a bit more complicated, but in the rational case, everything's nice because the Picard group of a projective rational surface is a lattice, and so you just get one linear system for each point in that lattice. Okay, so the upshot is, so we have our moduli space. So in particular, if we consider sheaves disjoint from Q, with a given Chern class, and let's say let's just pick some divisor disjoint from Q, representing that equivalence class of divisors. This maps to the corresponding linear system. Okay, but now we have the following. So the dimension of this linear system is one less than the dimension of the corresponding line bundle. And we can use the Hertzberg-Riemann-Roch theorem to compute this, and it's just something involving intersection theory of D and Q, but D dot Q is 0, so it ends up just becoming intersection of D. And what we see is that it's D squared over 2. And so this is half the dimension. One plus D squared over 2. This is half the dimension of the moduli space. And moreover, and the other way we can see this is that the arithmetic genus of D by the same sorts of intersection theory calculations is equal to the dimension of this linear system. So what this tells us is that our moduli space is something like the following. You look at divisors in this linear system, they're all just curves on your surface. And for each curve on the surface, we get some translate of the Jacobian. I mean, that curve has a Picard group, or a Picard scheme. And the Euler characteristic of M, if we fix that, tells you the degree of that line bundle. So, the typical sheaf in this family is a line bundle on a curve in this linear system. And so the typical sheaf is a point in the relative Jacobian up to possibly translated. So it's basically divisors of some fixed degree. So in other words, this gives us at least on an open set, we get a family of abelian varieties over a projective space. So this is a fibration of our moduli space. And the fibers, if you know symplectic geometry, when this makes sense, the fibers are Lagrangian. So this is the Lagrangian fibration, and this is analogous to the Hitchin fibration from which is basically the differential case. It's worth noting that the actual moduli space doesn't depend on Q. Or at least if we compactify in the obvious way, it doesn't depend on Q. I mean, here, of course, we should really be removing those divisors that meet Q, which, as I alluded to last time in response to Akani's question, is also basically the divisors that contain Q. So if we want it to be disjoint from Q, the divisor has to be disjoint from Q. But we can obviously compactify by throwing in those fibers. So that's not such a big deal. And of course, and the fibration doesn't really care then, what Q is at that point. The only thing that affects that is the actual symplectic structure on the fibration, where Q really, of course, plays a massive role. Okay. So we get this nice fibration. The other thing to note is that the support of our sheaf is unchanged by isomonodermy transformations. Because all those are doing is changing your sheaf by a point. And so, I mean, of course, that's a point on the real surface, but modulo, not having these really bad components pop up, these bad extra components pop up. So I should really say mostly. typically it's not changed by isomodulatory transformations when you do this, because all you're doing is changing the sheaf upstairs by some collection of points. And that's not changing the support. So this map, so this vibration is actually respected by our isomodulatory transformations. But what that means is that you are basically acting on this family of abelian varieties, at least generically abelian varieties, by translations, by a consistent family of translations. And so this pretty much directly leads to the observation that isomodulatory transformations should correspond to twisting by line bundles. Now, of course, the caveat here is this only applies to isomodulatory transformations if they're not changing your singularities, particularly. But we basically, the things we were dealing with exponents, we were shifting some exponents by 1 and shifting some other exponents by -1 in the differential case. But we're in the limit, the commutative relaxation, basically that, we're really shifting by h bar, and that's going to 0. So, and you can see that from the isospectral transformations, you really shouldn't be moving your singularities around. You can make them, you can add singularities if you're not clever about it, but you can't really move the singularities. And so the nice isomodulatory transformations are going to be automorphisms of your moduli space, or at least up to birational. Maybe only rational, but it should still be birational automorphisms of your moduli space. And they're supposed to respect this vibration, which means they're really acting on each of these, on the typical abelian variety in this family. And so it has to be translating by a section of this abelian variety over the function field of the linear system, basically. And so that's going to be twisting by some line bundle on the total space, which is some consistent family of line bundles on the curves in this linear system. And okay, maybe there are other ways of doing that, but it's hard to imagine a good way of doing that that doesn't involve just taking a line bundle on your surface. And then one can also check that twisting by line bundles does in fact give an isomodulatory transformation. And that's just because, well, if you twist by a line bundle, you can write that line bundle as a difference of sufficiently ample line bundles that are disjoint that are transverse to the support of your sheaf. At which point, when you twist up by the 1, you're just adding a bunch of points to your sheaf. You're just extending by a bunch of points. And when you twist down, you're just taking the kernel of the map to a bunch of points. And so those are both these natural isomodulatory transformations, and everything works. Okay. Now I should say this is something, this vibration picture completely breaks in the non-commutative setting, because it's based entirely on the idea of the support of a sheaf. And as I mentioned earlier, that just breaks in the non-commutative setting. And in fact, you see, for instance, if you look at, we know what the moduli spaces ought to be for the non-commutative case for Pan-Levé, because they're exactly these surfaces showing up in Sakai's hierarchy, and those don't have vibrations. So that's basically the situation there. Okay, so now I want to talk about this question of, how should we talk about divisors on the surface to sort of get a better idea of, what the possibilities are. If for instance, if I hand you a divisor class, one thing you'd want to know is, is it effective? Does it have more global sections than you expect, which would make this linear system bigger and break some things. Is it generically irreducible? Because otherwise, of course, you're going to have some special structure in whatever equations you get, which you might want to not have, or at least you want to take into account. And so the first thing we need to understand is the Picard group of your smooth projective anticanonical rational surface. So here I'm still assuming X rational, mainly because the rational cases where all the really interesting behavior happens. So you can make the theory work for the non-rational case, but it's not only easier, but richer in the rational case. Okay, so let me fix some additional structure. So, I mean, remember, X is coming from blowing up a ruled surface multiple times just to separate these sheets. So let me actually record the sequence of blowups. And furthermore, I want to record the final ruling, the ruling on this ruled surface X naught. So we have this structure. This is called I call this a Hirzebruch Berlot-Down structure. This is analogous to a notion of blowdown structure where you start with P2 instead of a ruled surface. But since not every surface we care about is going to be can possibly be attained as an iterated blowup of P2, and we care about the ruling anyway, it's better to end up with a ruled surface. So the point is, this is a ruling, and these are all monoidal transformations, i.e. blowups in single points. Okay, and then so two of these are equivalent. If we have consistent isomorphisms, and in particular, I allow a non-trivial automorphism of P1, because I don't care about the map to P1. I only care about the isomorphism class of the map to P1 for this picture. The reason for that is we'll see that this data is actually for the set of blowdown structures for a given surface is actually going to be discrete because we've modded out by the automorphisms of P1. Okay, so this is a blowdown structure, and this induces a partial basis. Well, in fact, a full basis, but let me first say it induces a partial basis of the Picard group of X, because blowing up a point always just adds a copy of Z to the Picard group. So pick of X is pick of X naught plus multiples of the first exceptional divisor, the exceptional divisor of X1 to X naught, plus multiples of the second exceptional divisor, and then finally multiples of the last exceptional divisor. And this is just standard stuff in that section of Hartshorne on surfaces. Okay, so to understand the Picard group of X, we just need to understand divisors on X naught. Okay, and pick of X naught is, well, non-canonically isomorphic to Z squared. And so it's a question of how do we choose a basis there. So one element is I call F, which is the class of a fiber of the ruling. I mean, if we're going to pick a ruling, if we're going to have a ruling as part of the data, we might as well use that as part of our constructions. We get this class of a fiber, and another is a class I'll call S min, which is the class of a section of minimal self-intersection. So the point is that X naught is P of a vector bundle on P2, on P1. But if we twist by that by a line bundle, we don't change anything. So it's really P of a vector bundle of the form structure sheaf plus O of minus D for some D. And let me call this, this standard name for this is FD. These are, so a ruled surface over P1 is called a Hirzebruch surface, and there's basically one for each non-negative integer. So this is the Dth Hirzebruch surface. Okay, and if you then trace through, this direct sum decomposition induces a pair of sections, but one of them is actually canonical, namely the one coming from the fact that this vector bundle has a unique global section, the quotient of which is a line bundle. And so that's short exact sequence induces a section of FD, and one can check that that section has self-intersection minus D. So if X naught is on FD, we have this section of self-intersection minus D. And the one place where it's not canonical is when D is 0, but that's P1 cross P1. And on P1 cross P1, well, you have a whole family of sections of self-intersection 0, but they're all linearly equivalent, so they give you the same divisor class. So that gives us one basis, namely S min and F. Now, it turns out this is not the most convenient basis to pick. And the reason for this is that there are we're going to see that there's going to be a lot of different blowdown structures. And as a result, and they're generally not going to preserve this D at all. And that would really mess up our combinatorics, make it a lot more complicated. So it would be better if we could come up with a basis that didn't depend on D. And we actually can do that, almost. So we instead use S, which is S min, plus basically D over 2 times F, or the greatest integer less than or equal to D over 2 times F. Okay, and so we get a basis of pick X, and we have intersection theory around. So this is not just a free abelian group; it's a lattice, and so we have this intersection pairing. And the intersection pairing, well, okay, EI squared is -1 because it's an exceptional curve. EI.EJ is 0 for I not equal to J because they're exceptional curves from different blowups. S.EI and F.EI are also 0. S.F is 1 because we have a fiber and we have a section, and they're necessarily going to meet at one point. A section meets every fiber in a point, so the intersection number is certainly 1. And the fibers, well, they're a fibration, so we can move within the linear system to get something disjoint. So it has self-intersection 0. And then finally, S squared is either 0 or -1, depending on the parity of D. So by doing this, by replacing S min by this slightly weird class, which well, it's always effective at least, but it's typically not a smooth curve or anything like that. But this gives us something where the intersection, the actual lattice we only get two possible lattices, no matter what ruled surface we start with. So the lattice only depends on, and lattice with basis only depends on d mod 2 and m, the number of points we blew up. Okay, so this is very handy because it means we can talk about this lattice, over the entire moduli space of surfaces, and it's nice and consistent. Or they surfaces with this kind of blowdown structure. Okay, now, blowdown structures aren't unique. So how can we change blowdown structures? Okay, there's a few different possibilities. One, let me phrase this correctly, if xi plus 1, i.e. the I plus first point getting blown up, is not in EI, then we can interchange the blowups. This doesn't change the surface. I mean, all this changing is the blowdown structure, but it does change the basis of the Picard group, of the Picard lattice. And what it does is it swaps EI and EI plus 1 in the basis. So it just swaps those two adjacent basis elements. Okay, and this is just the standard fact that if you take two distinct points and blow them up, it doesn't matter what order you blow them up in. So the only problem is if you blow up a point and then blow up the same point, i.e. a point on its pre-image, that you can't do this interchange. Okay, next thing we can do is we can x1 is a blowup of a ruled surface in a point. So we can blow down that fiber to get a new surface x naught prime, a new ruled surface x naught prime, which inherits the actual map to P1. Okay, this is a bit more complicated because it changes the parity, but so it acts reasonably on the lattice, and there's not. It's pretty easy to see what it has to do. You just need to work it out, but it changes the parity. So it changes odd to even, even to odd, and bigger. It also, it's an involution. If you do it twice, you get back where you started. So in other words, all I'm saying here is that if you blow up a point of a ruled surface, it's a blow up of a ruled surface in two different ways. And so we can swap those two ways. Okay. And then finally, if x naught is P1 cross P1, we can swap the rulings. And this acts by swapping S and F in our basis. Okay. Now, if we conjugate the swapping adjacent blowups, well, let's say E1 is the thing that swaps E1 and E2 by the operation of 2, i.e. an elementary transformation. We get something which preserves the parity because we conjugated by this thing that negated the parity. And we get an operation which is taking E1 to F minus E2 and E2 to F minus E1 and S to S plus F minus E1 minus E2. Okay, now this last operation seems a lot weirder than the other operations, but there's an observation. Each of these operations, well, each of these linear transformations of this sort of constant basis is a reflection. With respect to the intersection parent. And so particular, in each case, there's an element. So it's EI minus EI plus 1, or S minus F, or F minus E1 minus E2. And the transformation is just reflection in that element relative to the intersection parent. Okay. Now, formally, these generate a Cochlear group, which is, if you're not familiar with Cochlear groups, is basically a fancy kind of groups generated by reflections. And in particular, if you look at how these intersect, so we have S minus F, we have F minus E1 minus E2, we have E1 minus E2, sorry. So S minus F, F minus E1 minus E2, E2 minus E3, E3 minus E4, etc. And then we have one more sticking out here. So this is the standard convention for describing these Cochlear groups, which is basically you write down, you have a vertex for each generating reflection, and you draw an edge if the two reflections, if the group generated by those reflections is S3, and you don't draw an edge if they commute. So you get this diagram. And those of you who are familiar with Cochlear groups will recognize this family of diagrams. And what it is the Cochlear group EM plus 1. Now, this is not always familiar. There's only 3 of these that are really familiar to everybody. But basically, it's a sequence that starts off as A2, A1, A4, E5, E6, E7, E8, affine E8, and then it gets big. I mean, it gets really big. However, the affine case is infinite, but it gets really bad. And actually, of course, almost all the cases we're interested in are, to the right of this blue line. So, but there's this picture there earlier. So I should note, this is also, some of this is also familiar from an algebraic geometric context. So for instance, this E6 is exactly the E6 that comes up when you talk about the 27 lines in a cubic surface. I mean, so these surfaces here are at least generically cubic surfaces, and that E6 action really is, permuting the 27 lines in this nice way. And there are similar things for the E7 and E8 cases, and also the lower cases. Below that point, the group isn't as well behaved, but things are small enough, you don't really need the group so much. Okay, so we almost get an action of EM plus 1 on the set of blowdown structures. Of X. Now, the reason for this almost is, remember, these two operations we had, EI minus EJ, swapping EI and EI plus 1, or swapping S and F, only work some of the time. So particularly swapping EI and EI plus 1 only worked when the points were distinct. But we have the following nicer characterization of when we can do that. So observation. We can reflect in one of these simple roots. If and only if the corresponding divisor class is ineffective. So the point is, for the swapping two blowups, EI if xi plus 1 is on EI, then when you blow that up, you pick up a new divisor, which is the difference between the pre-image of EI and the new EI plus 1, the new exceptional curve. And so that's exactly telling you that EI minus EI plus 1 is effective. And then that's going to remain effective as you pull it back through each of consecutive blowups. Similarly, in the swapping S and F case, so that only works when you're even, of course. And you have you're an even Hertzsprung surface. And again, you notice that for an even Hertzsprung surface, if it's not P1 cross P1, then S is S min plus some number of copies of F, some positive number of copies of F. And so we can subtract F and it's still effective. So although we can't always reflect in simple roots, we can easily characterize when we can reflect in simple roots. So we get a Cochlear groupoid, if you like. Okay. Now, the significance of this being a Cochlear group is that there's a lot of literature out there on Cochlear groups. And particularly, there's a lot of algorithms about Cochlear groups. And one of the algorithms about Cochlear groups is a way of taking a vector in a fairly big space associated with the Cochlear group called the Tietz cone and simplifying it. And this also includes some similar algorithms, which is, for instance, given a root of the Cochlear group, or I mean, given something which might be a root, there's an algorithm that tells you whether or not it's a root. And this turns out to be the analog of this algorithm turns out to be extremely useful in our algebraic geometric context. So let me define the fundamental chamber. This is actually not quite the usual definition from Cochlear theory, but the fundamental chamber of pick X relative to this blowdown structure is the set of divisors D such that the intersection with any simple root is not negative. If you're too familiar with Cochlear groups, you'll notice that the sign is different from the usual Cochlear group thing. But that's because actually, if you look at these elements, all of these simple roots I've written down have self-intersection -2. So if you want to get something that's actually closer to the standard Cochlear group theory, you should negate the intersection theory, but that's fine. Okay, and so let me And the key point is that there's an algorithm for reducing things to the fundamental chamber, which is basically you start with any divisor, look for a simple root that it has negative intersection with, and reflect. Now, the issue is always that you can't always reflect, and so there's always some extra pieces of the argument, depending on exactly what you're trying to do, that take into account when you can't reflect. So let me give an example of this. So example. So suppose D is numerically a -2 curve. So it has self-intersection -2, and it's orthogonal from the anticanonical curve. Okay, and so the natural question is D represented by a smooth curve? Which of course would be a -2 curve. Okay. Now, the reason why this is significant is because we've seen that this is exactly the kind of case where you expect the equation to be rigid. And so, the hypergeometric function equation was rigid. This suggests that rigid equations in general are worth looking at. And so this turns into basically -2 curves. So we want to understand what the -2 curves are. And so figure we need to understand, if I hand you a divisor, when is it a -2 curve? Okay, well, what do you do? So let's reduce it to the fundamental chamber. So this involves repeatedly reflecting in simple roots with negative intersection with D. One thing that's worth noting is, although these reflections are all changing the Bloedon structure and not changing D, well, what ends up looking like in terms of this fixed basis is we're changing. It looks like we're actually changing D and applying the reflections to D. But really, the divisor class isn't changing. The surface is changing. Just the way we're getting as a blow up is changing. Okay, so what is this going to do? Well, the point is, as I said, we can't always reflect. So if we can reflect, there's no problem. Otherwise, well, let me give this simple root a name. Alpha. Alpha is effective. And D dot alpha is negative. So they have a component in common. But this implies that either D is alpha or D is not a -2 curve. So if you try to reflect in something and you're not allowed to, either it's because you're trying to reflect in yourself or you're not a -2 curve. Now, one thing that's slightly more annoying for these big groups is this procedure is not actually guaranteed to terminate in general. So we need something that'll tell us when we need another condition that tells us, yeah, we can't possibly be a -2 curve. So notice that F is Nef namely, which means that basically the restriction of f to any curve has non-negative degree. Okay, and this is just, it's clearly true on ruled surfaces, and you just check that it survives being blown up. Okay, so this implies that f dot d must be non-negative if d is going to be a -2 curve, because in particular, if it's -2 curve, it's effective. Okay, now this group we have, well, so again, if you're familiar with Cochlear groups, you'll notice that if we remove this funny root s minus f, what we're left is just a dm type root system. And in particular, if we don't use s minus f in our reflections, well, if we don't use s minus f, the process must terminate. And then if we want to reflect, in s minus f, well, s dot d minus f dot d is negative. So s dot d is less than f dot d, and reflecting reduces f dot d. And thus we're going to terminate either by trying to reflect in d itself and saying, yeah, okay, it's a d is one of those, d has now become a simple root of our blowdown structure, or because we've made the intersection with f so small, we've made the intersection of f negative because we've reduced it too many times. And so in particular, we see that any -2 curve is a simple root for some blowdown structure. Okay. So one thing I should say is I've been using this basis. Sorry, just because it's convenient, but there's an analogous basis that works if you have it for an odd blowdown structure, just conjugate by an elementary transformation. Okay, so, okay, another example is -1 curves. If this is a -1 curve, then there exists a blowdown structure by the same algorithm, basically, such that d is equal to em. And this implies any two even blowdown structures are related by a sequence of reflections. Well, in particular, legal reflections. Because what we can do is we can take the last exceptional divisor of the one blowdown structure and apply reflections to the other blowdown structure to make the last ones agree, and then induct and make the second to last ones agree, third to last ones, etc. And then eventually, well, we've blown down these same curves, and so we have to end up with the same ruled surface. And worst case, we have, if it's P1 cross P1, we may have to swap the two rulings. But there's clearly only two blowdown structures on P1 cross P1. So once we've gotten down to a ruled surface, we're done. Okay, so what we see basically is that the blowdown structures, therefore, are something like a homogeneous space for this big reflection group. I mean, modulo the fact that this issue of not always being able to do reflections. Okay, and of course, this is also true for odd blowdown structures, because any even blowdown structure, at least assuming we've blown up more than 1 point, or at least 1 point in that case, any odd blowdown structure is related to an even blowdown structure by an elementary transformation. And so the same thing is true for odd blowdown structures. So the groupoid itself is connected. The full groupoid of blowdown structures, if we include elementary transformations, is connected. If we only include these reflections, then it has 2 components, one even, one odd. Okay. Another example. So let's say d dot q is 0, and d is nef. And then we want to know, well, we can always find a blowdown structure such that D is in the final blowdown chamber. And here the point is that, well, it's still true that D dot F is non-negative because F is effective and D is supposed to be nef. It's supposed to have non-negative intersection with every curve. And if alpha is effective, then d dot alpha is non-negative because it's nef. And so we don't want, so anytime we see an effect, we have an effective simple root, we don't want to reflect it. And so again, we can just do this algorithm. This puts us into the fundamental chamber. Now, the significance of this, so as we do this process, when we swap S and F, we're changing the structure of our equation. And particularly, we're changing the order of the equation. And so particularly what we see is that this operation minimizes d dot f over all blowdown structures. And thus this corresponds to a sort of minimal interpretation of this sheaf as an equation, or of a sheaf with that divisor class as an equation. Okay. So, right. So the statement about minus 2 curves tells us that rigid equations corresponds to roots, or in fact, well, yeah, roots of EM plus 1. And moreover, those roots have to be disjoint from the anticanonical curve, which adds some extra conditions. But it moreover gives you an algorithm if I hand you a divisor class for telling whether it's rigid. This algorithm is similar to an algorithm of Nick Katz in his book, Rigid Local Systems. The main difference is that Katz's book never leaves the differential land. And in particular, there's always, well, firstly, it's only about Fuchsian equations, but it also never leaves the land of differential equations. And so it's the operations it's doing are basically something that's called middle convolution. Although I've been told that the term gets misused a lot, but I don't fully understand why why it's misused. But anyway, it's usually called middle convolution in the integral systems literature anyway. And whereas the algorithm coming from this Cochlear theory is not going to preserve the type of the equation in general. So not only does it change the order, but also changes the type. And so you could very well get a case where you start with a differential equation, do this reduction, and end up with a difference equation. Okay, but if you actually look at Katz's algorithm from this perspective, you realize, although we didn't state it this way, it is in fact an algorithm of the same kind associated to a different cognitive group. So it really is a very similar flavor. Okay. And then the Neff statement actually lets us find finitely many different possible D in the fundamental chamber such that D dot Q is 0 and D squared is 2G minus 2. Or in other words, if you specify the dimension you want and then do this operation to put yourself in the fundamental chamber, there's only finitely many possibilities, with one exception, except for G equals 1. So G equals 0 is basically the -2 curve statement. That's, it's just saying that basically, well, sorry, there is one more thing to say there, which is that, remember I mentioned that this swapping S and F is basically doing an integral transform. Whereas these other operations are essentially just bookkeeping on the surface. They're just recording different ways of writing your surface as a blow up of a surface relative to the same P2. Sorry, same P1. But because of the issue that sheaves don't have completely canonical, they're only sort of up to scalar gauge in general interpretations, it tends to be the case that if you do this F minus E1 minus E2 reflection, that tends to introduce a scalar gauge transformation. But what you see though is that these operations we're doing are either doing nothing because we're just swapping adjacent blowups, and so we're just reordering the blowups. It's pure bookkeeping. They're doing this one reflection in F minus E1 minus E2, which is at worst a scalar gauge transformation, or they're doing this integral transform. And so what we see is that in the -2 curve case, so G equals 0 case, every rigid equation has an integral representation, formally at least, for its solutions. What I mean by this is that if you do this procedure for a general -2 curve, which is not, as long as it's not like already a simple root, then what you're going to find is that we're first reflecting in the dn part. So we're doing stuff that doesn't change the degree of the equation. We're just doing scalar gauge stuff. And then we're doing a reflection S minus F to reduce the order of the equation. So we keep doing that. And so we see that the only way we're going to be forced to stop is when we try to reflect an S minus F, we're going to see that we already are S minus F. But S minus F basically corresponds to the trivial equation. And so there's a sequence of scalar gauge transformations and integral transformations that reduces our equation to the trivial equation. And doing the reverse takes the trivial equation and turns it into the rigid equation we want. And so in particular, a scalar gauge transformation is just multiplying by a solution of a first order equation. And then we apply the integral transform, multiply by the solution of a first order equation, apply an integral transform, etc. And so there may be a bunch of steps, but we're going to end up with an integral representation for a solution of the equation in this way, because we can write down a solution of the trivial equation, namely 1. Now, this is only formal in general, because already the representation as integral operator is already only formal. I mean, it's a perfectly well-defined action on difference operators or differential operators. But if you try to actually have it act on functions, you tend to get annoying convergence issues. I mean, even the Fourier transform, you have issues. You need to have some boundedness things, and certain nice functions like 1 don't have nice Fourier transforms. The Fourier transform is a distribution. So there's definitely convergence issues there. And in fact, the only case where I can actually do this without encountering convergence issues is in the top case, the symmetric elliptic case, where you can basically write everything as contour integrals and have enough control over the poles as you go along that you can prove you can always do the next contour integral and it'll still solve the next equation. So when I say every here, I actually mean every elliptic if you want to be completely rigorous about it and have an actual integral representation. On the other hand, this does at least formally explain, for instance, the Euler integral representation for the Gauss hypergeometric function. And if you do this procedure and sort of write down what the integral operator ought to be, and what the sequence of integral transforms is in that case, and then apply it to your favorite solution of the trivial equation, you exactly get the Euler integral. So this really does explain a lot. Similarly, the reason they're called hypergeometric functions is because they're a sum of a series, and the ratios to consecutive terms are, the k plus first term over the kth term is a rational function in k, which means that the terms themselves satisfy a difference equation, a rational difference equation, in this case, first order. And what one sees is that that itself is also an integral transform. It's basically the inverse of the power series solution transform, or the Mellon transform. Well, it's either Mellon or inverse Mellon, one of the two, but it's essentially that same transform. And so we see that is itself an integral representation of typical these hypergeometric functions. And so you can get some higher order hypergeometric functions in the same way. And those equations also, if you check them, are again rigid. So the NFn-1 equation is also a rigid differential equation. And there are analogs for multiplicative elliptic, etc. So, okay, so that's what we get from -2 curves, is essentially an explanation of what the heck is going on with hypergeometric functions. And, and an idea of sort of how we can at least start to classify hypergeometric functions. Okay. And then in the NEF case, again, what it tells us is that up to doing these integral transforms and these scalar gauge transforms, so relatively nice operations, we can reduce any lax pair into one of these lax pairs that's in the fundamental chamber. And since we didn't change the surface, we just changed the interpretation, we're still going to have the same family of isomonotropy transformations. And so this gives us a way of cutting down some of the possibilities. On the other hand, it also gives us a way of producing new possibilities where we just say, okay, well, we'll start with something in the fundamental chamber and then leave the fundamental chamber, and you can get some higher order things. So now, as I said, there's an exception for g equals 1. So what happens for g equals 1? Well, we want d squared equals 0, g dot q equals 0, and we want it to be in the fundamental chamber. And we also want it to be NEF. But mostly that's just imposing extra conditions, so it's not a big deal. I mean, it's only imposing extra conditions on special surfaces, so it's not a terribly big deal generally. Oops. Okay. What we need, it turns out, if you just look at the inequalities that have to be satisfied and then just basically solve them, we find that D is a multiple of Q. I'm assuming it's positive because otherwise that's not a very interesting equation. Now, so the thing is, all of those work. And so what we see is that we get a lax pair for Pain-Levé. And when I say for Pain-Levé, I mean anything in the hierarchy will have a lax pair of this kind of rank 2R instead of R, which is such that all singularities have multiplicity R. And then the degree of the equation, if we want this to be irreducible, we're going to need the degree of the vector bundle to be prime 2R. Now, when I say you get a lax pair for Pain-Levé, you have to be a little careful. What you get is a family of linear problems with a two-dimensional moduli space. One can then show that that moduli space is actually rational, which is actually turns out to be a non-trivial statement. And an even less trivial statement is that then when you look at the various isomorphism transformations you get from that, they actually agree with Pain-Levé. Now, of course, I'm also definitely palming a card here because this is everything here has been about the commutative relaxation. When I talk about a lax pair for Pain-Levé, of course, I'm talking about the non-commutative picture. But everything I've said, you can make work in the non-commutative setting. So in particular, you still have this notion of the fundamental chamber and these algorithms for reducing to the fundamental chamber in the non-commutative setting. And so these minimal lax pairs still arise. Now I'll say a little bit more later about the nature of these lax pairs and why they really do agree with Pain-Levé. Okay, so this is the one case where you get infinitely many. So next interesting case, G equals 2, G equals 2. Well, then there's two possibilities. One possibility is this particular divisor class, which if you translate everything back, basically says you have, at least in the generic case, you have 10 singular points that are also, firstly, it's a second order equation, is what that 2 is telling us. It has 10 singular points because we blew up 10 points. And all of the singular points have multiplicity 1. So it's basically the Fuchsian case, if you like, although the 10 singular points is at the elliptic level. At the differential level, the simplest differential level, when it's Fuchsian, you'll have 5 singular points, each one of which has 2 exponents attached. And then you can always sort of gauge things to make one of those exponents 0, up to twisting at the infinity or something. So this is basically Garnier, the 4-dimensional Garnier case. And there's another case you get. where you have 7 singularities with multiplicity 2 and 2 singularities with multiplicity 1. But now your equation is rank 4. And this is the matrix Painlevé case. Now there's a paper, I forget who all the co-authors are, that classifies 4-dimensional moduli, basically differential equations with 4-dimensional moduli spaces. Or in other words, classifies 4-dimensional isomonotony equations. And if you look at their classification, you'll see that they have a bunch of, in addition to a bunch of second-order equations and fourth-order equations, they have some third-order equations. They have equations of various other orders popping up. And the reason for that is because they're looking for the minimal differential lax pair, whereas this is giving us the minimal differential or difference lax pair. So in particular here, you'll note that if you swap S and F, that'll give you a third-order equation. And that can change the type of the equation. So if you're in one of these cases where, it starts out as additive, but the analog of the Fourier transform turns it into differential, i.e. the Mellon case, you'll exactly get a third-order differential lax pair, but the minimal lax pair will actually be second order. So by allowing these difference lax pairs, you can make you allow your lax pair to actually end up being a lower order equation and simpler in some respects. Okay. Another thing I should note here is that here, in the Garnier case, the ruling is actually uniquely determined by the, there's a unique choice of ruling that's compatible with the minimizing blowdown structure. And it's just basically, you look at what reflections are left over that can preserve this class. So what are the simple roots that are orthogonal to it? So you can reflect that and not move it out of the fundamental chamber. And you see that all of those reflections preserve F. It's just basically the dn. And so they're all just basically doing these scalar gauge transformations. They're not really changing the equation in a terribly significant way. So you really get so in these Garnier cases, you get a unique lax pair. Whereas in the Painlevé cases, where it's like I should say here, of course, Q squared is 0. So M is 8, and we're in the affine E8 case. And so that case is, sorry. I know I'm making you all dizzy. In other words, it looks like 2s plus 2f minus E1 minus et cetera down to E8. And this is now orthogonal to the entirety of affine E8. And so you get a lot of different lax pairs that are still minimal, because you can act by this entire affine E8, although only the finite part of E8 ends up actually really affecting the qualitative structure of the equation. But what this does tell you is that you do end up getting multiple lax pairs for a given Painlevé equation. In particular, if you do the combinatorics, so what you find is that although there are, I believe it was 22 types of Painlevé equation in the hierarchy, there are, I believe, 61 different lax pairs, or qualitatively different lax pairs. And I'll talk a bit more later about how one can actually try to classify the different types of lax pair for a given, because, well, basically now that once you specify one of these divisor classes, you can basically ask, okay, well, now I can take any surface on which that divisor is still an F, and then that gives me a moduli space of equations of the correct dimension, and gives me a family corresponding isomonotony equation and a corresponding lax pair. So you can, so in particular, what this, for instance, we get an elliptic Garnier by taking this at the very top level, but we also get an entire hierarchy. And so then we can try to ask, and we'll ask later about, how do you classify the different, the different levels in this hierarchy? What are the different types of equation that can actually arise here? Okay, both of these extend to higher genus. And of course, we keep getting more and more cases as genus gets big and there's a combinatorial explosion and so on and so forth. Okay. So this is, so this fundamental chamber idea really is very helpful. In particular, we can also determine which D, which are orthogonal to the Q, have smooth, or let me be precise, integral, that is irreducible and reduced. When are they represented by integral divisors? And here, there's two ingredients. One is the reduction to the fundamental chamber, and the other is a paper of Harborn that tells you in purely geometric terms when a divisor class orthogonal to the anticanonical divisor is generically integral. And then you just basically take his conditions and notice that they can be expressed in purely combinatorial ways once you're in the fundamental chamber. So almost anything you want to know about a divisor class on one of these anticanonical surfaces, rational surfaces, you can answer by moving it to the fundamental chamber and then using some general statements about the fundamental chamber. And there's always just some extra details about how you move to the fundamental chamber. So this includes there's algorithms for computing the cohomology of a given line bundle, for telling if D is effective. And I think those are the other two big things. And then both of those cases, you just get this extra complication that when you're trying to reflect by a route you're not allowed to reflect in, you have to do something more clever than just argue that you don't care. And so you need to basically figure out how to do that. So for instance, in the effective case, you say, okay, well, there's some component in common, and you just need to figure out sort of what the common component has to be so you can subtract it. But it turns out you can do that algorithmically, and then you've subtracted it, and now you keep going. And then similarly for computing the cohomology, you basically just need to show that if you're trying to reflect, you can subtract that component in common and control how that affects completely control how it affects the cohomology. And so again, you end up with something reasonably well behaved. So okay, so those are the main things. This is probably a good place to stop. So let me stop here and throw the floor up to the questions.
So maybe could you explain again, or how we explain that reason why -2 curve corresponds to the rigid equilibrium?
Oh, okay, yeah, so that was from last time. Basically, so there's this general formula, the Hertzberg-Riemann-Roch formula.
Yes.
That, well, okay, I guess it's often only stated as it tells you the Euler characteristic of a line bundle.
Mm-hmm.
But you can then easily, it's not too hard to extend that using the notion of Grothendieck group to tell you the Euler characteristic of the x from one sheaf to another. So basically, you take the x0 minus the x1, the dimension of x0 minus the dimension of x1 plus dimension of x2 in the surface case.
So you're just saying that the corresponding sheaf is rigid.
So yeah, so the point is that the sheaf has, basically that's the condition for the sheaf to have trivial self x1.
Mm-hmm.
And no, non-trivial automorphisms, because that would split it up and let you deform pieces separately. So there's some extra arguments about why you want it to be a line bundle on a -2 curve, and not something on some more general sheaf that just happens to have a bunch of components that are -2 curves. But that's basically because if you had something that had multiple components, you could change the degrees of those components, and so you could get different sheaves with the same invariant. So it would be infinitesimally rigid, but not actually rigid. And so that's why you want it to be irreducible. But basically, you just see from Hertzberg, Riemann-Roch that it has to satisfy. Well, it has to be disjoint from Q because that's our ground assumption that we've separated all the singularities, and it has to have self-intersection -2 because you want the Euler characteristic of the self X to be -2. Sorry, to be 2, because you have to have one for the endomorphisms and one for the dual of the endomorphisms.
I see.
And so you always have that 2 built in, or the -2, once you've taken into account that the Mukai pairing is the negative of the intersection pairing, basically. And so that tells you that the -2 case is when it's rigid, and then more generally, if the self-intersection is 2G -2, then the dimension is 2G. At least the expected dimension is 2G. But in fact, if it actually is disjoint from Q and is simple, that is no non-trivial endomorphisms, then the dimension will actually be 2G, and it'll in fact be smooth because the dimension is always what you expect.
Also, I have another question. It's not the main point of today's lecture, but you have said you don't have the notion of the support for the non-commutative setting. But isn't it not? Is your non-commutative surface not deformation quantization?
Well, so the tricky thing is that so if you want to preserve the notion of support, I think if you do an infinitesimal deformation that becomes non-commutative, then you have a reasonable chance of carrying along support. But the problem is what we're doing, we're actually extending things along an algebraic scheme. I mean, basically, it turns out that the non-commutative deformation parameter is actually a line bundle of degree 0 on the anticanonical curve. And so as we go, so once we've gone a finite distance away from the commutative case, there really is no way of defining a. And basically, the problem is what we're actually deforming is not the geometric object. It turns out what you actually are deforming in these cases is the category of sheaves.
I see.
And there's basically no way of basically it comes down to this issue of we don't really have invariant open sets. When you have a translation by Q, you don't have invariant open sets. And so you basically don't have a way of covering your surface by things that are independently getting non-commutative deformations and then gluing them back together. It really is a much more global thing in general. Now, if you've blown up a smaller number of points, like if you're looking at there are a few cases where you could do something simpler, and that's actually what the original literature on non-commutative algebraic geometry was all doing, is basically in a number of cases what you can represent your projective scheme as the proj of a graded algebra, and take a flat deformation of the graded algebra. But even in that case, if you look at it, you see that you can't really just glue that together out of pieces to get something that's that's still not in general glued together out of affine pieces. But it turns out in general that the surfaces we care about is, well, basically, unless Q squared is positive, which will, and in that case, the only sheaf we're going to see are going to be rigid sheaves, if that are disjoint from Q. So it's not we don't consider all of the interesting isomorphism stuff. But basically, so unless Q squared is positive, you don't have any sort of nice representation as a graded algebra even And so you just get this more abstract thing of there's an abelian category and it with a marked object, which is the structure sheaf.
So you
but since we care about sheaves, having the abelian category is enough for most purposes.
In your category, you don't have any deformation parameter, you mean?
Well, no, I mean, so you get a family of them. And so basically, so you get a family of, and basically it's a, so the, okay, let me get really technical here. The moduli stack of non-commutative surfaces is a fiber bundle over the moduli stack of commutative anticanonical surfaces, where the fiber is the relative pick knot of the anticanonical group.
No, sorry. What I mean is, you in your category, you don't have deformation parameter h bar.
Oh yeah. No, I mean the deformation parameter is, in general, well, so basically, we have these three types of equations. So, well, sorry, four types of equations. We have differential, where the parameter is h bar in the additive group.
Yes.
We have ordinary difference equations, where the parameter is h bar in the additive group. And that's basically because it turns out using these integral transforms, we can turn any ordinary difference lax pair into a differential lax pair and vice versa, possibly at the cost of making our singularities worse, or the equation higher order. Okay. In the Q case, the parameter is an element of the multiplicative group. And in the elliptic case, the parameter is a point on the elliptic curve. So yeah, I mean, basically what you don't have, or what you only have in the difference case is sort of this extra transformation where you can rescale the deformation parameter. That you definitely don't get in the beyond the additive case.
You cannot take h bar goes to 0 in those settings?
Well, no, I mean, you can take the limit, but the difference between the additive case and the multiplicative case is that in the additive case, you can multiply h bar by a scalar without changing anything, because you have to rescale all your parameters. And so you can take a limit as h bar goes to 0, where all the fibers are the same.
I see.
Until you get to the actual limit. Whereas in the different, so basically, so you get this sharp limit where you're sort of going from your differential case and then immediately ending up in the Higgs case. In the multiplicative and elliptic cases, you don't have that sort of isotrivial kind of degeneration. So you can still take that parameter to 0. I mean, it's a curve in your family in the moduli stack. So you can certainly take a limit along that, and that'll give you one of these. That'll give you a Poisson surface. But it's not going to be. It's not an isotrivial degeneration anymore.
So in those elliptic case, your consideration about Hitchin type relaxation and so non-commutative settings are not so related.
Well, right. I mean, basically, well, so what's true, and I'll be saying more about this, is that at least I mean, depending on your numerical invariance. So I mean, to specify a component of this big moduli space, you should really you're specifying a Chern class of your sheaves and an Euler characteristic for your sheaves. And depending on the Euler characteristic, and basically, well, if a certain GCD condition holds, or if your Euler, well, then you can actually prove that the Hitchin moduli space, or the Hitchin style moduli space, you can prove that that's rational. And if the Euler characteristic is 0, that basically corresponds to the case of a connection on a generically trivial vector bundle. And so there's an open subset of that moduli space, which is the same as the moduli as an open subset of the moduli space of actual equations.
I see.
And so that tells you that the moduli space of actual equations is also rational. And it even tells you that you can use the commutative theory if you can construct a universal parameterized family in the commutative theory, that then you just change Q, and that gives you a corresponding family for your difference, for your, Q difference or elliptic or ordinary difference or whatever equations.
Mm-hmm.
So you do get useful information. I mean, there definitely are relations between them.
Mm-hmm.
And actually the deepest relation along those lines, which ends up being fairly important for some of the later theory, is that if you look at this non-commutative surface, which as I said is really just an abelian category corresponding to, it's a deformation of the category of let's say, coherent sheaves
Mm-hmm.
on your original surface. So you look at the derived category of that.
Mm-hmm.
So the structure sheaf is an exceptional object in the derived category.
Mm-hmm.
And so it induces a semi-orthogonal decomposition. So basically you have, so in other words, there's a subcategory of the derived category, which is things that have completely trivial global sections, even when you derive the global sections.
Mm-hmm.
Okay, and so that's a nice triangulated subcategory.
Okay. Yeah.
Okay, that triangulated category is independent of the non-commutative parameter.
Mm-hmm.
So it's actually the same category as you would have gotten if you started with a particular commutative projective surface and done the same game of looking at things with no global sections. So there really is. So even though there's not this, there's not this C infinity type connection around, there really are some quite deep connections between the commutative relaxation and the non-commutative case. In particular, you can use this to basically very easily write down the derived category of the non-commutative surface, because you just basically you have these two pieces and you just need to specify how they're glued together. And it's basically it turns out all you're doing is you're twisting, I mean, they're glued together in a particular way in the commutative case, and you're just twisting that by a line bundle at degree 0 on the anticanonical curve.
Mm-hmm.
And so makes the derived category very easy to write down. And actually a lot of the arguments in the non-commutative setting end up in basically working with that kind of description of the derived category, along with a nice inductive description of the T structure.
Mm-hmm.
So,
Mm-hmm.
but yeah.
Yeah.
So no, I mean, there is actually, and there's a lot of places where, yeah, the argument really does involve saying, yeah, okay, let's reduce to the commutative case.
So
using this kind of transformation.
So back to the original question. So
yeah,
my question was somehow, so even though, how to say, so for non-commutative setting, by for a module over the non-commutative surface, by reducing it to the commutative setting, can you define the support?
Well, so basically the problem is that since the surface is changing,
mm-hmm.
there isn't a canonical way of extending your surf. I mean, you have this curve in the family of surfaces, but you have this sheaf on over one point of that curve. There's no canonical way of extending that sheaf along the family.
I see.
So this is where this isotrivial deformation is important, is because if you have an isotrivial family of surfaces, there's a canonical way of extending the sheaf, and that gives you a sheaf over the generic fiber, and then there's a canonical way of extending that to the special fiber.
Yeah, but
that doesn't work when nearby fibers aren't actually related surfaces. You can extend the sheaf, but you have an entire 2D dimensional family of ways to extend the sheaf to the nearby fiber.
But by using that relation between abelian categories, you cannot.
So the one case in which you can sometimes talk about support is when your sheaf has Euler characteristic 0. And so if you have, but that's the case where it is already birational to the commutative moduli space. And so you can basically define support, at least rationally, as you map it to the commutative moduli space and then take the support. But that's the only case in which you can do that, because it's only the things that have trivial R gamma that are in that category that's independent of the deformation parameter.
I see.
So those cases you can move to the commutative surface, but not anything else.